Okay, we've got our electron configurations of atoms. We've got our electron configurations of ions. We talked about atomic radius. Now we're ready to talk about ionic radius. So, it's going to be measured in a similar way, but it is the what's a radius? It's the distance from the nucleus to the outer shell. How you measure that is a little tricky, but this is going to be a discussion about the radius of whether it's a cation and an anion and how they compare to each other. How does a cation's radius compare to its atom? How does an anion's radius compare to its ion? And then we'll look at, well, we'll tell you what we'll look at after that. Let's not go too far. Cations, let's think about this. We're going to be able to compare the radius of these if we were to think about the number of electrons and protons in these two guys. So lithium versus lithium 2+. I'm sorry, I don't want to be lithium 2+ because that would be weird. Find it on your periodic table. Let's see if I've got a periodic table here. Yeah. So if we look at lithium and we were to consider how many protons it has, okay, that's the number that comes right off the periodic table. There are 3 protons in lithium and there are 3 protons in lithium plus, because you don't change the number of protons. But the number of electrons is a different story. If we're talking about the atom, atoms have the same number of protons as they have electrons. So there's 3 electrons in lithium. If you consider Li plus, on the other hand, it's a plus charge because you lost electron. So we only have 2 electrons. And we took out the outer shell. So let's just, for just a minute, think about this. We have the 3 protons in the nucleus. We had the 2 electrons in the 1s shell. For lithium, the 3rd electron was here, being shielded by these guys. We took this electron out to make lithium plus. Now these electrons aren't very good at shielding and they're filling that +2 charge. What would you think would happen to the size when you turn into a cation? So thinking about what I just went through as an argument, I want you to choose which would have the larger radius. Would it be lithium the atom or lithium plus? Well, I'm very hopeful that you put lithium the atom would be larger. Lithium the atom has that electron in there, right? It has that electron. It is being shielded by those. It is feeling less of a pull of the nucleus because those electrons are there. Lithium plus, we are removing that, and now we're considering just these electrons being attracted to that nucleus. They are feeling that +3 charge pretty well, and they're going to be smaller. But you do not have to go to this level. If we just think about electrons in general, I have 3 protons trying to hold on to 3 electrons. But here I have 3 protons and they're just trying to hold on to 2. It is so much easier to pull 2 electrons in than it is to pull 3 electrons in when you're a +3 charge. So this will always be, when you move electrons, it will always be smaller. So that is always the trend. Okay, if you look here, always, cations are much smaller than their corresponding atoms. So what you see in gray is the size of the atom. What you see in that, we'll call it maroon, all right, that's the size of the ion, and it is much smaller. And as you've just removed only 1 electron as we've gone down this first group, we're just comparing removing 1 electron. And it's still a whole lot smaller. Over here, we're removing 3 electrons, okay? But we're just removing that outer shell in every case. And so it's getting smaller as we drop into the size of the inner shell. All right, let's compare for anions. For anions, we're going to consider a similar argument, but we're going to compare F versus F minus. So F minus, the number of protons versus the minus number of electrons. Okay, so I think I have a periodic table here so I can find fluorine, and I know that it has 9 protons. Whether it's fluorine the atom or fluorine the ion, it has 9 protons. Fluorine the atom will have 9 electrons. So those 9 protons in the nucleus are attracting all those electrons in the shells out to there. Now over here I'm adding one more electron. So now I've got those 9 protons trying to hold on to 10 electrons. So thinking about that, which one do you expect to be larger? 9 protons holding on to 9 electrons, or 9 protons trying to hold on to 10 electrons? Well, hopefully you said B. B is going to be the larger one because it's more difficult for the 9 protons to attract and hold on to 10 electrons. It likes being this way energetically, but it's going to be bigger. So it is always the case that anions are going to be not just a little larger, and it's not because it's crowded, but we have got another electron we're putting out in that shell, and we're going to end up getting larger as those nuclear protons are having to hold on to more electrons. All right, so we can see that size increasing as you simply put on, in the case of the 7A family, 1 electron. In the case of the 6A family, you're putting on 2 electrons. So here we're seeing that flip-flop. When you take the atoms and you turn them into ions. Lithium, the atom; fluorine, the atom. Now fluorine is much smaller than lithium, even though it's got way more protons, okay? We've got 9 protons, 9 electrons, 3 protons, 3 electrons, and that was the argument of the effective nuclear charge. As we go across the periodic table, we know that they're getting smaller and smaller. So lithium is much smaller, much larger than fluorine, even though it has a lot more electrons. When they transfer that electron, so lithium says, you know what, I really would like to be a +1 charge. This is my preferred state energetically. I would like to get rid of that extra electron. And fluorine says, well, I'd like to have a noble gas configuration. I'll take your electron and I'll become F-. So we do this electron transfer process. But look what happens to the size. The fluorine gets much bigger than the lithium just by that transfer of that 1 electron there. The next thing we need to look at is something called an isoelectronic series. So we need to define the term isoelectronic here. Or review, I guess, the term. I don't remember defining it before, but this is what isoelectronic means. It is atoms that have the same electron, atoms or ions that have the same electron configuration. So they don't just have the same number of electrons, but they have the same electron configuration. That's what isoelectronic means. So get that definition down. I'm not certain, while it says remember, I'm not certain that we have covered that before. So we're going to consider atoms and ions that have the same number of electrons and consider the trends of them. The only way you can determine them is, again, to look at the number of protons versus the number of electrons. They're all going to have the same number of electrons because they're isoelectronic. So we're going to compare a series where they all have the same number of electrons, but their number of protons are going to be changing. And if you increase the number of protons in the nucleus, you're increasing the nuclear charge. You're going to be able to make a comparison of which one do you expect to be larger and which one do you expect to be smaller. Now we're going to look at an example of these 4 ions, S2-, Cl-, K+, and calcium 2+, in order to do this. So I'm going to make a similar table to what I've been doing before. We have S2-, we have Cl-, we have K+, and we have Ca 2+. Now if we look at a periodic table, we can determine the number of protons and electrons of each of these guys. So sulfur has got 16 protons. So we're doing the protons first. Sulfur has 16, chlorine has 17, potassium has 19, and calcium has 20. So then we can consider the number of electrons each one has. Now this is a 2- charge, so it has 2 more electrons. This has 18 electrons. This has 18 electrons. This is an isoelectronic series, so they all have 18 electrons. This had 20 protons. We've removed 2 electrons from the 20 it would have as an atom, and that makes it 18. So this is how many electrons they have. So these are isoelectronic. So now you can look at these guys, look at their number of protons. They're each trying to hold on to 18 electrons, and think about who is going to be more effective at holding on to electrons and therefore pulling them in tighter and making it smaller. So you're going to pick which one of these is the largest and the smallest in this series. I hope you pick D, because D has definitely got S2 minus, the largest. 16 measly protons are trying to hold on to these 18 electrons. The nuclear charge is pretty small holding on to those electrons. Here we've increased the nuclear charge up to 20. We have that nuclear charge of 20 holding on to the electrons. They all would have the same shielding. They would all have the same inner shell of electrons. So it's the nuclear charge is going up, and therefore it's going to get much, much smaller. Now, this is where students go awry with this problem. They're used to looking at a periodic table to come up with trends, because we learned that if we had a periodic table, and I'll draw out a little periodic table here. Okay, there's our periodic table. We learned that it gets smaller as you move across, and it gets smaller as you move up. But that is for atoms. That is not when you're comparing ions. What students will do sometimes when they're working problems like this is they will find these ions on the periodic table. So let's move over and find them on the periodic table. We've got our S here, our Cl here, we got our K here, we have our Ca here. And they say, well, I know it gets smaller as we move this way, and it gets smaller as we move up, and they're going to want to rank things according to that trend. But you can't do it, because that trend is for atoms, and these are comparing ions. Calcium plus, potassium plus, calcium 2 plus, sulfur 2 minus, chlorine minus. So when you are doing isoelectronic series and you are trying to determine sizes, or anytime charges are getting involved in your comparison, don't look at the periodic table trend. You want to compare the number of protons to the number of electrons and make a judgment. Number of protons to the number of electrons and make a judgment. The only time that the periodic trend really holds true, and let me pick a group of ions here. Let's say we were comparing lithium plus to sodium plus to potassium plus. As long as we're in the same group and we're talking about the same charge, then the trend that we know is going to hold true. These are going to get larger as we go down, or smaller as we go up. All right, that says larger. It's too small for you to read. Larger as you go down. You can make that comparison, because we've removed the valence shell electron in every case. We're looking at the noble gas core in every case, and it's just going to get bigger as you move down. But otherwise, comparing atoms to ions, comparing an isoelectronic series, you've got to look at the number of protons and the number of electrons in order to decide who's larger and who's smaller, and don't just look at your periodic table. That's the biggest mistake I see students make over and over again when they're asked to compare the size of these. Let's see, I think that is all we have for this discussion. Oh no, I just do want to show you this. This is just certainly nothing to memorize, but spend a little time looking at this table. We see over on the right-hand side the ions. They're always so much larger than the cations. On the left, we see their normal cations that you have. And let's look at something that I have not brought up, but you ought to be aware of. When you're comparing ions, if you remove more electrons, so this is 2 plus versus 4 plus, it does get smaller. This is 62 compared to 71 right there. So let me see if I can make it increase there, that we can see it better. So the SB5 plus has got a radius, ionic radius is 62. The SN4 plus, it's 71. Removing that additional electron did make it get even smaller. We see the same thing holding true here with iron 3 plus and iron 2 plus. As we remove another electron, it gets smaller. That's always going to be the case. All right, so that's the end of this lesson.